I'm Quentin Grossetti. I'm here to present this paper called the Homophily-based approach for fast post recommendation in microblogging systems. Sorry, a long title. It's from my PhD that I'm currently finishing at University Pierre-Marie-Curie. And so as a very short introduction, I will talk about the growth that microblogging platform have faced this last decade. So I think we all know this fact, but basically Twitter is now up to 700 million of messages published every day, and Instagram is 17 million of pictures published every day. And by microblogging platforms, what we mean is systems where people can fully choose to follow each other and can share content on this social network. So the question that this platform ask themselves is basically how can we connect users to relevant content? So I think this is all the goals that we are trying to achieve here. And can we use traditional models on this kind of platforms? So basically, there is a lot of challenges. For instance, for content-based systems, where we want to extract meaningful features from items. Actually, microblogging systems, micro means small, in the sense that tweets, even if they have doubled recently, now they are up to 280 characters. It's hard to have meaningful features from messages. Collaborative filtering method, I will go very fast because of the 15 minutes limits. The problem of collaborative filtering methods is that actually the matrix is very big, and therefore computing like all the similarities between user or between items can be very long. And the matrix is also more sparse, I think, than most matrix that we know in recommender systems. And also systems like matrix factorization that are really suitable nowadays and that are really doing very good results have this problem of taking time to do this work of factorization, and therefore maybe you will be too slow to achieve a recommendation on fresh messages. So this is why it's there is another reason, but I will go deeper into this later. Social recommender systems, meaning using friends to do some recommendation, blending models by adding a personal relationship into the recommendation. Actually, the problem on Twitter, for instance, is that there is no meaningful connection between people. You don't follow Barack Obama because he's your friend, actually. So this is why it's hard to blend to use those kind of models. And one model that Twitter presented 2 years ago now, which called GraphJest, based on random walks model. Basically, the idea is to use a bipartite graph. So we have users on one side of the graph and tweets on the other side. And every time that we will have an interaction between a user and a message, we will add an edge in this bipartite graph. And the main idea is basically to do random walk and to rank messages based on the number of times you stop on them. So basically the problem, it's not a real problem, but we are thinking, okay, but in order to keep up with fresh content, what Twitter does is erasing all links because it needs to move on in some sense. And maybe it's a shame not to use all the interactions that users had in the past. So actually I think they are now going full towards deep learning methods, but they haven't published yet a paper on those new systems. And so, before describing our model, our idea was first to collect a large data set from Twitter, because we are in public research. We don't have access to a large data set from companies such as Twitter. So we had to crawl it ourselves. I don't know about the legal aspects of this, but this is what we did. And basically, we have a data set of more than 2 million of users and close to 3 billion of tweets. And so on these data sets, we did some analysis, such as which mostly are already known. But for instance, if we count the number of times messages are retweeted or liked, we see that a large number of messages are actually never retweeted or liked. Another fact is another analysis we done is the lifespan of messages, meaning the time elapsed between the publication of the message the message and the last time it was shared or liked. And as we can see, close to 50% of messages are actually dead before 1 hour. And it's really unexpected for a message to go after 3 days, showing that Twitter is like really oriented over really fresh contents. So this is what recommender system needs to take in account. Maybe it's a difference, I guess, with Deezer, for instance. Recommending an old album is probably okay, but a message from 2 years is probably not good. And another analysis we've done is to combine both similarities between users and distance in the network, based on the idea that are people that have high similarity close in the network or not. Actually, what we found is that, okay, they are closer if there is a direct link between them, but they represent a very small portion of people having similarity with you. And it's even more clear if we just rank the most influential user to the 5th most influential user. As we can see, most of the time, there is no direct connection. So we are thinking, because Twitter is a small network, and therefore, when you go to up to 3 hop distance, you can achieve to grab all the network. If we stop just before, at this 2 hop distance, you can see we can get up to 70% of the top 5 most influential users. So from those analysis, we concluded that basically it was really important to be able to compute a recommendation score just after the publication, or in our case, the like of or share of a message. So really real-time recommendation. That few users have actually high similarities. The scores are really low, actually. Meaning that maybe we can use transitivity to kind of enhance to fight the data sparsity, let's say. And the third conclusion is that we can use this 2 hop distance in the network to find the most interesting user, and therefore make the scope of calculations shorter. So this is what we've done. This is a Twitter network. Okay, so this is an oriented graph. Users follow each other. And for every user of this network, in this case you, we will take his followers, and the followers, is following, sorry, and the following of his following. So we are at 2 hop distance from this node. And in this set of users, we will compute the similarity between you and those users. And then we will build an artificial network with this similarity information. So we now have an oriented weighted graph with, on the edge, the similarity between users. And the idea is just to apply a small propagation model on this network. So the model takes into account the probability of the people that are influenced to you in the network. So I will give a really small example. So this is our similarity network. A tweet is published, and because there is no connection between this message and the network yet, we don't really care about it until there is a like or a share, and then we infer the fact that the probability that this user likes this message is 1, and we propagate this information towards in our network. So now the probability that W will like this message is 0.25, and now the probability that you like this message is 0.06. Basically, you get the idea. So we can show that this model is actually convergent, and we can apply several optimization on this model to speed up the convergence step by applying some threshold work. And also, what we found out a little bit experimentally is that we had to limit strongly messages that were really popular, because they were recommended to everybody. So we had kind of like a curve to follow the distribution of popularity of messages. So it kind of makes sense for recommender systems to give a boost for messages that are unknown, and to decrease the popular audience of messages that are really popular, that already found their audience. And so the experiment we done on 130 millions of retweet actions. We split it in 90% and 10%, so this is really common in academia and I guess in a lot of industry. And we tried to predict in the test trial of 10% for 1,500 users the prediction of retweet. So we compared ourselves with a naive collaborative filtering method because we also use a kind of similarity between users. So it was interesting for us to see if transitivity in our systems could do better than those approaches. We compared with a probabilistic model from bias, and GraphJet, the Twitter use solution, still in place. I think so. So results show that actually our solution, which is in yellow, performed really good. Except in the end, so on the bottom line, you have the number of recommendations we make daily for user. So the recommendation on the test is for like 44 days, something like that. And number of hits, meaning number of prediction of messages that were in the window of recommendation that were actually retweeted by the user. And so we find that at the end, for really large value of recommendation per day, I mean 160 recommendations per day is quite a lot. Collaborative filtering methods, naive, can still be better than us. When we look a little bit closer into the results, we can see that actually GraphJet tends to recommend popular items. It's probably due because of this random walk model, where basically it will tend to stop on mostly popular items. And bias does the opposite by recommending really low popularity items due to this propagation in the natural Twitter network. And we can see that actually our model and a naive collaborative filtering approach both have a mix of both. This is the F1 score. So as we can see, we have a peak value around 20 or 30 recommendation per day, meaning maybe it's an accurate value to the recommendation because we know that this is the time, the frame that we will have more chance to do hits. And we also compared ourselves in terms of computation time. So I won't enter really into the details, but basically bias and collaborative filtering methods are really slow. Bias for the actual recommendation process and collaborating filtering method for the initialization step, meaning computing all the similarity between users. And GraphJet is really cheap and doesn't need any initialization time, which is cool. And we succeed by being a little bit faster than the GraphJet solution. And the last question that we wanted to answer was how can we stay updated because of we do propagation on an artificial network. We need to take in account the fact that people will continue to follow new person, likes new message. So how can we keep up with this modification at low cost? So basically there is 4 possibilities. The first is do nothing. The second possibility is to recompute our similarity network from scratch. The third possibility is to update only the weight on your similarity network. And the last step is what we call crossfold, because we haven't found a really better name. But it's to apply our 2-ops exploration and construction of edges, not on the Twitter natural graph, but on already built similarity network. And actually what we found is that this crossfold strategy is doing quite good because we have like almost the same results as recomputing everything from scratch, but for really cheap computation time. So this is possible because we have this convergence property, meaning if we apply this system of 2-ops exploration on the same graph over and over again, we see that after 3 steps, 4 steps, the graph is kind of like full. We don't add more edges. So in conclusion, I show how we have a method relying on homophily to find the nearest neighbors at low cost, because we won't search for the whole database of users, but only for the closer ones. We can use transitivity to fight high sparsity, and that our model outperforms state-of-the-art solution. And I also show how we could update this model for really cheap, and I kind of follow a good improvement in it. Okay, but thank you very much, and thank you Recsys for the meetup and Deezer for the hosting.
Well, thank you, Quentin, for the presentation and volunteering last minute.
You're welcome.
Okay, questions now.
I have a question about Bayes, because Bayes is a method, it's not a model. So first, what's your model?
Yeah, you're right. Yeah.
And second, when you say it was slow, I mean, since it's just a way of specifying things, it's not a way of resolving things.
Sure. Yeah.
So what implementation of
actually,
solving for it?
I don't recall the exact title of the paper, but there is a paper which use like bias model, methods to do recommendation. I will give you like the name of the article, and we just implemented the solution basically.
Okay, thanks.
Maybe easier question. You said that 92% of tweets never get retweeted.
Yeah.
And 40% die after 1 hour.
Yeah.
Wouldn't it be less than 8% that die? I mean, like if you tweet
okay,
something.
so sorry, I didn't explain that in the lifespan. I just don't take in account messages that are never retweeted because they
so
will have a
those,
lifespan
have at
of
least
0.
One retweet
yeah,
last
exactly.
less than an hour.
Yeah.
Okay, there was one other question, but I've forgotten it. So.
Okay, no problem.
Yes.
Thank you for the presentation. It's quite interesting. I'm not very familiar with the GraphJet algorithm. How does the GraphJet and your algorithm take into account the fact that people can follow someone and they can be followed back? So which creates, I guess, a relationship that is much stronger than just following someone or just being followed. How is it captured by your model?
I think it doesn't actually. I'm not sure this is something that is used. Actually, what they use is your circle of followings. Also, because sometimes they won't start from your exact position to do the random walks, but from people closer to you, and they have like the system to do like similarity between users and to start more from those users more frequently. But I don't know about something like you said.
Because it creates like loops in your graph, right?
You mean for the random walk?
Yes.
Yeah, but because this is a bipartite graph, I think it doesn't really matter because you have like a chance to go the same direction. I'm not sure. Maybe, maybe I don't know.
Maybe they just go in loops.
I mean, there is low chances to do this because you will have a chance to go in another direction at some point. So.
Okay, is there another question? Yes.
When you tested your method, you said that the tweets that you recommend got retweeted a certain amount of time. How did you test that? Like you're not actually able to recommend tweets on Twitter.
Okay, so yeah, you mean like about this figure?
Like how did you
Okay, so basically in our data set we have like 130 million of retweet action on messages that have at least twice shares. Yeah. Okay. So we split this, we rank this set of retweets by the oldest to the freshest, and we remove the 10% the fresher, and we compute the training on the 90%, and we try to predict if the message that were actually retweeted in real life we were in the recommendation window.
Okay, but those are messages that are already like getting into someone's feed because they're following somebody.
Yeah, absolutely. Yeah. I mean, the perfect recommendation system should theoretically be at 0 hits because it shouldn't give you message that you already see. So this is a way for us saying, okay, maybe all the rest of messages are also relevant because we have a high number of hits. But I mean, this is a very, it's a very good question. I mean, yeah.
Okay, so I have one question. We've seen that your method uses the fact that with Twitter you can reach almost all a large number, amount of the community with 2 hops.
Yeah.
If we have another kind of data where more hops are needed, do you think that it could work, or should we adapt it?
Yeah, I mean, for us, the fact that Twitter is a really small world is actually a problem, because we don't have a lot of choices to do hops. Either you do 1, either you do 2, either you do 3, and you reach everybody. So I think the more hops you can, you have, I mean, like the more average distance between users is the biggest it is, the best it is, because then you can say, okay, I will stop at maybe 4 hops, or like you can have like a decision based on the profile of the user, maybe on some this kind of strategic that we just cannot use with Twitter, because after 3 there is nothing left.
Okay.
But I'm not sure. I mean, it really depends on the data, I guess.
I guess in the topology of the graph is that you have very large hubs, like you have some people
this
followed
is,
by
this is
everybody.
traditional small world.
And does it mean that when you recommend, if one of these hubs retweets something, it means that it will probably impact a large number of users?
Actually, not really, because we don't give high. I mean, it's, in a sense, you will if this person likes a lot of stuff or shares a lot of messages and is very popular person, then yes, he will have some sort of higher power enough model. Actually, I was interested into this idea, and I computed like the most influential user in this network. And I don't know why the most influential guy in our similarity network is Seth MacFarlane, the author of Family Guy. I don't know why, but maybe like funny jokes, and he has like he shares a lot of things. But yeah, this is actually the kind of thing you're talking about here.